Hey Ramblers, this is the first of two videos which will cover chapter 1.5 in our textbook and deals with trigonometric functions. We're going to start the video out by talking about radians, and we'll use radians to define the sine function, the cosine function, and how those two functions define tangent. We'll look at the graphs of sine and cosine and talk about two concepts you probably remember from pre-calc, amplitude and period. The last thing we'll do in this video is look at the general function for any kind of a sinusoidal curve like sine or cosine, and then the different parts of that general function and what they do to shifting the graph on the Cartesian plane. You're going to find that in calculus we don't deal as much with the unit circle as we do with the sine and cosine graphs on the coordinate or the Cartesian plane. So maybe a little bit of an adjustment for you. Alright, I hope this video helps. Please pause often, take notes, and thanks for watching. We're going to start our discussion of trig functions, sine, cosine, and tangent, by first looking at what a radian is. Now, a radian is just a unit of measure, like degrees, but we use radians in calculus because it makes the derivatives of sine and cosine and tangent come out much more nicely. Now, that isn't much of an explanation now, but when we get to chapter 3, I'll explain it in a little more depth. So what is this radian? Well, a radian is defined to be the angle at the center of the unit circle which cuts off an arc length of 1. So the arc length is going to be the distance on the circle itself, and when that distance reaches 1, the angle that it creates at the center is said to be 1 radian. Okay. You'll recall that the circumference of a circle is 2 pi r. So the circumference of a unit circle, which has a radius of 1, is going to be just 2 pi. Now, if we want, we can figure out what a radian is relative to a degree by noticing that there's 360 degrees in a circle, and that would have to be equal to 2 pi radians, because after all, the distance all the way around the circle is the circumference of the circle. And if that's 2 pi, then that has to be equal to 360 degrees. Now, so let's solve for the right side. If we divide both sides by 2 pi and simplify, we'll get 180 over pi is equal to 1 radian. So that's 180 over pi degrees. Now, if you figure that pi is equal to about 3.14, that means that that's like 180 divided by 3, so that's going to mean that it's about 60 degrees. And if you look up at our picture, you can see that sure enough, 1 radian does look like it cuts off an arc length of 1, and that angle there at the center is probably about 60 degrees. Okay, let's move on then and take a look at sine and cosine on the unit circle and how they relate to x and y. Let's consider the unit circle for a minute. And if we were to rotate the arm that starts at the initial position where the end of the arm is at 1, 0, and we begin to rotate that arm around the unit circle in a counterclockwise direction, we get this diagram here, where the radius is that arm I'm talking about, and it's at point P. So that forms a triangle. And we use that reference triangle. As you can see, it's a right triangle. So this angle down here that we're calling T, if we were to look at the sine of angle T, it would of course equal opposite over the hypotenuse. Now, the opposite side is the y coordinate. So the sine of T equals opposite, which is y, over the hypotenuse, which is just 1. So that's why we say that the sine of t equals y. We could do a similar thing with cosine, where we'd say that the cosine of the angle t is equal to the adjacent side over the hypotenuse. Well, since the adjacent side is the x-coordinate or the x-axis, that's going to be x over 1. So we say that cosine of t just equals x. As useful a learning tool as the unit circle is, we don't really use it much in calculus. So let's try to make a connection between the unit circle and what we do use in calculus, which is the graph of sine and cosine on the Cartesian plane, or which is just the xy plane. So here on the right side of this diagram, I have the unit circle, and it looks as though it's on the plane or the Cartesian plane itself, but it's really not meant to be. It's just there on the side. So what I want to do is think about how what we said in the last slide, that y equals sine of t, not as a function, but that the height of an arm or of a point P, the y value would be sine. So its coordinates would be cosine of t, comma sine of t. And the y value would be the height above the x-axis. And as the arm moved its way around the unit circle, these y values are going to get taller and taller until you get to pi over 2, or 90 degrees. And at that point, at pi over 2, sine will have hit its maximum. And then as the arm continues, the height of the point is going to get smaller and smaller until once again it's at 0. So halfway through the circle, the height of the point can be sketched out, and if we were to record them and plot them versus time, or versus the angle, we would see that we have a curve that looks like that, which was the first half of the sine curve. Now, if we continue, we'll see that the height of the point becomes negative in the next quadrant, and that's exactly what the sine curve does. We get to a minimum value of -1 as the height at 3 pi over 2, and then as the arm continues into the next quadrant, we see that we get back to 0. So let's take a look at that, drawn out more graphically, using this GIF file. You can see that as the arm begins to turn around, as it begins to rotate, it traces out the sine curve. Now we could do a similar thing with cosine, but cosine, of course, is equal to the x-coordinate. And when the arm starts, the x-coordinate is at 1, 0. So cosine starts out up there at 1. And as the arm rotates, cosine gets smaller until at pi, which is halfway around the circle, it's at x equals -1. Then as it moves into the lower half of the circle, the x-coordinate gets smaller and smaller, or I should say its magnitude gets smaller and smaller, so its absolute value, until at 3 pi over 2, which is 3/4 of the way around the circle, we have an x value of 0. And then as the arm continues to rotate back to its initial position, we get back to the x value of x equals 1. So while I don't have a GIF that draws out the cosine function, these are two functions I want you to be clear on. And it's important to recognize that cosine is the sine curve shifted pi over 2 to the left. Okay, Ramblers, let's keep on moving on, taking a closer look at amplitude and period of these functions. The graphs of sine and cosine are what we call sinusoidal. That is, they're periodic. They move in waves that repeat. All sinusoidal functions are characterized by an amplitude and a period. We can calculate the value of the amplitude and the period from the graph by using the definitions. Amplitude is half the distance between the maximum and minimum y values. So we can see here on the graph that we have a y value of -2 and a maximum y value of +2. So to find out what the amplitude is, we just take half of that. So that would be 2 minus -2, and since it's halfway, we divide by 2. So not surprisingly, 4 over 2, and we get an amplitude that's equal to 2. So the amplitude is going to be the height of a wave from the middle or the depth of a trough. It's either one. On the other hand, the period is the smallest time needed for the function to execute one complete cycle. So here on this graph, we could say that the period is from the bottom of this trough all the way to the bottom of this trough. Or maybe you'd want to make it from the middle of the wave, where it crosses the x-axis, I'm sorry, the t-axis, to the middle of the wave where it crosses the t-axis at 3. Either way, you can see that we're extending from 0 out to 4, so the period of this function would be 4. Had we calculated it along the t-axis, we would have gone from -1 to 3, which also would have been 4. So the period for this function is 4. Okay, the general form of these sinusoidal functions is given by f of t equals plus or minus a, and then whatever the function we're talking about, sine or cosine, times b, and then in parentheses you'll have t plus or minus h, and at the end plus or minus c. Obviously, if you're talking about cosine, you'd put cosine in where the sine had been. Okay, so let's deconstruct this a bit and talk about it, especially in terms of what we talked about in the last section, where we were shifting functions. The amplitude, which is again half the height of the wave, is going to be the number in front. It's going to be the absolute value of a. The period is not going to be b, it's a common misconception, but it's going to be 2 pi divided by b. Then the horizontal shift will be what takes place inside the parentheses. So if the b is not factored out, you have to do that first. The h has to be by itself without the factor of b in there. And then the vertical shift is always easy to pick out. That's just what's going on at the end. Now keep in mind, the horizontal shift is always in the opposite direction of the sign of h, just like it is in the last section when we're shifting regular functions. Okay, let's take a look at a function, an example, and see if we can't figure out what the equation is for it. So this equation here, we know that f of t is going to equal, well, it looks like a cosine function that has been flipped upside down. You could also say it looks like a sine function that's been shifted horizontally. You can go either way, but I'd rather deal with flipping a cosine over than dealing with the horizontal shift. I think that's the most complicated part. So I'm going to say that this is equal to the negative of cosine, and I'm going to put an amplitude in of 2, because to me the amplitude is clearly 4. I'm sorry, half of the height of the wave to the trough is 4, so half of that will be 2. So -2 cosine, and then as I try to figure out the period, I can see that the graph repeats itself every 4 units. So to determine b, I'll say that 4 equals 2 pi over b. Solving for b, I get b equals 2 pi over 4, which of course simplifies to pi over 2. All right, so in my parentheses I have pi over 2t. Now since I decided to make this a cosine curve inverted instead of a sine curve shifted horizontally, I don't have to worry about a plus or minus h. So I'm going to just close my parentheses, and in this case, since the center of my curve is right along the t-axis, there hasn't been any vertical shift, so I don't have any c to deal with. So my final equation is going to be f of t equals -2 cosine of pi over 2, sorry about that, pi over 2t. It's worth talking about the tangent function separately, because there's a small difference between the tangent function and the sinusoidal functions. First of all, while the amplitude is still the number in front of tangent, it doesn't make as much sense to talk about the amplitude of the tangent function, and here's why. As you can see from the tangent graph, there is no maximum or minimum. So when we talk about the amplitude, it doesn't really make sense. Now, when we put a constant in front of tangent, it will stretch the curve. So, for instance, something like f of t equals 5 tangent of t would be a steeper curve, but it would still keep repeating like this. It would just, the curve would be much steeper. It's also really important to note that the period of tangent is pi, that it repeats every pi instead of every 2 pi. And finally, when we generate the curve of tangent, it has all these asymptotes. And let's take a quick minute to explore why that's true. Tangent is defined as sine over cosine. And even back to the SOHCAHTOA days, where sine equaled opposite over hypotenuse and cosine was adjacent over hypotenuse. And we knew that tangent, of course, was opposite over adjacent. Well, if you took the sine and divided it by cosine, you would be dividing the fractions of opposite over hypotenuse divided by adjacent over hypotenuse. And you recall from your Algebra 1, when you divide a fraction by a fraction, heck, this is even arithmetic, when you divide a fraction by a fraction, you flip the second one and multiply. And when you do that, the h's will cancel out. And so you'd be left with opposite over adjacent, which is tangent. And so you can see how we arrive at tangent by thinking it as sine over cosine. Well, that has important implications for the graph, because we're going to have an asymptote everywhere this denominator of cosine is equal to 0. And cosine equals 0 at negative pi over 2 and pi over 2. And all of the multiples of pi over 2, I should say all of the odd multiples of pi over 2. So as we start to figure out the tangent function, just be aware that you're going to run into asymptotes anytime cosine would be equal to 0. Now, we won't do as much of this as you did last year with pre-calc, but it is just important to be aware of the salient parts of the graph. Okay, that's all for this video. There's been a lot in here. We'll pick up with inverse functions on the next part of this video in this chapter. Okay, Ramblers, thanks for watching.